Download this code from codegive.com, link in the description below. Dynamic programming, assembly line scheduling problem explained. This tutorial dives deep into the assembly line scheduling problem, a classic example of how dynamic programming, DP, can be used to optimize a decision-making process. We'll explore the problem's definition, its underlying principles, how to formulate a DP solution, analyze its time and space complexity, and provide code examples in Python. 1. Problem definition ***. Imagine a manufacturing facility with two parallel assembly lines, line 1 and line 2. Each line has n stations. A product needs to go through each of the n stations, in order, to be fully assembled. The time it takes to complete a specific station can vary between the two lines. Furthermore, there's a transfer cost involved in switching from one assembly line to another between stations. The goal is to determine the optimal path through the stations on both lines that minimizes the total assembly time. Formal definition ***. N** the number of stations on each assembly line. **Aij** the time required at station J on assembly line I equals 0 for line 1, I equals 1 for line 2, J equals 0 to N1. **Tij** the transfer time required to switch from assembly line I to the other assembly line after completing station J. I equals 0 for line 1, I equals 1 for line 2, J equals 0 to N2. Note that transfer time is only relevant between stations, not after the final station. **EI** the entry time to assembly line I equals 0 for line 1, I equals 1 for line 2. **Xi** the exit time from assembly line I equals 0 for line 1, I equals 1 for line 2. Example ***. Let's say we have two assembly lines with 4 stations each. Here's a possible configuration. Station 0, Station 1, Station 2, Station 3. Line 1, A0J, 7934. Line 2, A1J, 8564. Transfer, T0J, 231. Transfer, T1J, 423. Entry time, EI, 24. Exit time, XI, 32. In this example, *A00 equals 7, time to process at station 0 on line 1. *T01 equals 3, time to transfer from line 1 to line 2 after completing station 1. *E1 equals 4, time to enter line 2. *X0 equals 3, time to exit line 1. 2. Why dynamic programming? This problem is ideally suited for DP because it exhibits two key properties. Optimal substructure ** the optimal solution to the problem can be constructed from the optimal solutions to its subproblems. In other words, the fastest way to reach the nth station is based on the fastest way to reach the n1 th station. Overlapping subproblems ** the same subproblems are encountered multiple times during the computation of the overall solution. For example, calculating the minimum time to reach station 2 might require knowing the minimum time to reach station 1 from both lines, which itself might require knowing the minimum time to reach station 0. Dynamic programming avoids recomputing these overlapping subproblems by storing their solutions. 3. Dynamic programming formulation ***. We define two auxiliary arrays. *T1J** the minimum time to reach station J on line 1. *T2J** the minimum time to reach station J on line 2. Base case *. Asterisk T10 equals E0 plus A00, entry time to line 1 plus time at station 0 on line 1. Asterisk T20 equals E1 plus A10, entry time to line 2 plus time at station 0 on line 2. Recursive relation asterisk. For J0. Asterisk T1J equals min, T1J1 plus A0J, T2J1 plus T1J1 plus A0J. Asterisk this means the minimum time to reach station J on line 1 is the minimum of. Asterisk the minimum time to reach station J1 on line 1 plus the time to process at station J on line 1. Asterisk the minimum time to reach station J1 on line 2 plus the transfer time from line 2 to line 1 after station J1 plus the time to process at station J on line 1. Asterisk T2J equals min, T2J1 plus A1J, T1J1 plus T0J1 plus A1J. Asterisk similar logic as above, but for line 2. Final solution asterisk. The minimum total assembly time is min, T1N1 plus X0, T2N1 plus X1. Asterisk the minimum of. Asterisk the minimum time to reach the last station on line 1 plus the exit time from line 1. Asterisk the minimum time to reach the last station on line 2 plus the exit time from line 2. 4. Building the optimal path, optional, backtracking. The above formulation gives us the minimum time. If you also want to know the sequence of stations that lead to the minimum time, you need to keep track of the choices made at each step. You can do this by creating two additional arrays, L1J and L2J, which store the line number, 0 or 1, that contributed to the minimum time at station J on line 1 and line 2, respectively. After calculating T1 and T2, you can backtrack from the end, using L1 and L2 to reconstruct the optimal path. 5. Code example, Python. Explanation of the code asterisk. 1 assembly underscore line underscore scheduling, A, T, E, X, N, function asterisk. Asterisk takes the assembly line data as input, described in the problem definition. Asterisk initializes T1, T2, L1, and L2 arrays. Asterisk handles the base cases, T10 and T20. Asterisk iterates through the stations using a for loop, from station 1 to station N-1. Asterisk inside the loop, it calculates the minimum time to reach the current station on each line, using the recursive relation. Asterisk the L1J and L2J arrays are updated to store which line, 0 or 1, contributed to the minimum time. Asterisk after the loop, it calculates the final minimum assembly time by considering the exit times. Asterisk backtracking asterisk it reconstructs the optimal path by iterating backward from the last station, using L1 and L2 to determine which line was used at each station. Asterisk returns the minimum assembly time and the optimal path, a list representing the line to use at each station. 2 example usage asterisk. Asterisk defines sample data for A, T, E, X, and N. Asterisk calls the assembly underscore line underscore scheduling function to get the result. Asterisk prints the minimum assembly time and the optimal path. 6. Time and space complexity asterisk asterisk. Asterisk time complexity asterisk O, N. The algorithm iterates through the stations once to fill the DP tables and then again to backtrack. Asterisk space complexity asterisk O, N. The algorithm uses T1, T2, L1, and L2 arrays, each of size n. If you only need the minimum time and not the path, you could optimize the space to O1, by keeping track of only the minimum times for the previous stations, instead of storing all the T1 and T2 values. However, Backtracking requires storing these values, so you can't optimize if you need the path. 7. Optimization, space. If you only need the minimum time and not the optimal path, you can significantly reduce the space complexity from O(n) to O(1). You only need to store the minimum times to reach the previous station on each line. Here's the modified code. In this optimized version, we only store T1_previous and T2_previous, representing the minimum times for the previous station. We update these variables in each iteration of the loop. 8. Real-world applications ***. While simplified, the assembly line scheduling problem models scenarios in various industries. Manufacturing optimizing the flow of products through different stages of production. Computer science, job scheduling assigning tasks to different processors or threads to minimize overall execution time. Logistics finding the most efficient route for a shipment through a network of distribution centers. 9. Summary The assembly line scheduling problem is a great illustration of dynamic programming. By identifying the optimal substructure and overlapping subproblems, we can formulate a solution that avoids redundant calculations and efficiently finds the minimum assembly time. The ability to reconstruct the optimal path provides even more value, giving insight into the best sequence of operations. Understanding this problem provides a solid foundation for tackling other optimization challenges in diverse fields. Remember to consider space optimization if you only need the result and not the path itself.